It is what physicists tend to call an ideal rope. An ideal rope has three characteristics. An ideal rope is frictionless. It is massless. And it is stretchless. So first off, frictionless, it's not going to cause the pulley to turn. Massless, I don't care about the weight of the rope. Stretchless, if A moves, B moves, if B moves, A moves. A and B are moving together. So I'm not going to have a situation where A is staying still while B is attached to a spring and starts moving downwards. They will move together. In physics 151 and 251, we would eventually do away with frictionless. In 251, we would potentially do away with those depending on how much time we have. But this is 110, we won't do that. The pulley is also ideal, though with a frictionless rope, not particularly crucial, but the ideal pulley it is massless and frictionless. Now recognize in a real pulley, you've got two things rubbing against it. The rope would be rubbing against it in real life, and then also wherever the axis of rotation is would also be rubbing against it, and there's no friction in either place. The super pulleys, which you'll eventually deal with in lab, are as close as we get. If you use some of the older pulleys, and sometimes they're out and students start using them, those are not frictionless. Clearly not frictionless. All right, to do the force diagram, let me break it down into the type of things that we're going to work on here. We got box A. We have the ground with the pulley attached. Now when I do this, I'm indicating that the pulley is part of the ground. Some students will want to do forces as if the pulley is a separate object. It's not inherently wrong, just unnecessary. B, and then those are the objects. With the checklist. And right off the bat, can we get rid of anything?
Other.
Yeah. Now personally, I like starting with weight. I would say, let's say, since tension is the new one, let's wait on that one. But if you want to start with a different, tell me a force acting on what? And in which direction?
B.
What about box B?
The force of the Earth.
So the weight of the box.
Weight of the box.
Okay. So I got weight acting there, weights of B. They come in pairs, where's the other part?
Or
That way on the ground, yeah. All right, one pair done.
Would box A be pulling?
Say it again.
Box A be going down?
Okay. So basically repeating except for A. That we're doing this. Well, we get as far as you said. And the other part?
And then it would be going up. Pulling the box.
Going up on, where am I drawing the arrow?
Up to the box. Box A.
Up on the box? Is that,
From
I'm
the-
having trouble hearing you.
From the ground to the box. Draw
From-
the arrow from the ground up towards the box.
Like that?
No.
That upward force is acting on what object? The ground. So I'm drawing it on the ground. Now, it doesn't have to be right below where A is. Again, all of this is the ground. If you want to put all your weights in together, that's fine, or spread them out. It's easier for me personally to keep track if I sort of draw them roughly in line with the other one. That's it. The rope is massless, so it does not have weight, so we are done. Now, if you as a student decide that you want to draw a weight down acting on the rope, it is not wrong. What you would see on the test if you gave weight to the rope is I would probably circle it, and then I would write something like that. That is IGN for ignore. I'm going to ignore it. So on the test, if you see some scribble like that, that just means I'm not marking off for it, I'm just not counting it.
Do the arrows of weight have to be below the ground?
Does the,
You know how the arrow is like touching the?
no, I just need it,
Because like in that one, it's like coming above, in this example, it's like.
yeah, no, that's fine. So it's
Okay.
just so long as it's clear, those are the forces acting on the ground.
Okay.
Those are the forces acting on the ramp. That's what's acting on the box. Yeah, just don't draw it in no man's land.
Okay, gotcha.
I should say completely in no man's land. All right, weight's done. Normal.
Should it be, since perpendicular? Should be up and down. Against the
Exactly.
box for B,
Up and down against box B.
yeah,
What is it touching?
the ground.
B is not touching the ground. No, B is suspended.
Oh, yeah, so then A, sorry.
All right, yeah, I'll buy A is touching the ground, definitely normal force there. So up and down, up on A or up on the ground?
Up on A, yeah, up on A.
Up on A, yeah, all right. So Y is an A, and then down on the ground. All right, they're definitely touching.
I don't understand that part. Can you like help me understand the normal force?
All right, normal force is what keeps one object from going through another.
Okay.
If there were no normal force acting on me right now, then I would just fall.
Okay.
But the floor is holding me up. That's the normal force. So here, you can just sort of imagine if suddenly there was a cave in and all of that disappeared. What would A do?
Fall.
But it's not falling because that hasn't happened. So something's got to be holding it up. That's the normal force, holding A up.
Okay.
And that's why I think Hewitt calls it the support force, because it's supporting.
Oh, okay. So no normal force for B. No normal force for B, because it's not touching, okay.
Right. There is another pair of normal forces though. We do have two other objects touching.
Is it the pulley and the rope?
Yes. This rope is not falling. I mean, this part might be going down, but the rope is not in free fall. Something is keeping the rope from being in free fall. So the actual direction of the normal force acting on the rope, you got some flexibility. The rope touches the pulley from here to here. So the direction of the normal force on the pulley is going to be somewhere in this region, range right here. I did not give you enough information for you to know the exact direction. So, but, you know, just, it's somewhere in that direction. Call it Y sub R for rope. And then the other part of that would be acting,
That way on the pulley.
yep. So I want to draw the opposite direction of that, give it the same label. Probably the most common mistake I see at this point is people forgetting about the pulley and rope. Pardon?
Does the arrow have to go all the way through the pulley?
No, no, just somehow indicate that it's acting on the, technically, that's part of the ground, so somehow the force is acting somewhere in that direction. All right, normal force, done. Friction. Wherever there's a normal force pair, there might be friction. I have two normal force pairs, so I have two places to look.
Box A in the ground.
Okay, which way is the friction going to be acting on box A?
Two.
Towards the box. Or,
It's either going to be left or right.
Say to the right, because the rope is attached to it.
So remember, friction opposes the direction
So to the
that it
left.
wants to move.
Okay.
Which way does A want to move?
to the
To the right,
Therefore, which way will friction act on it?
to the left.
And then the other place where we have a normal force pair. What about friction at the pulley rope connection?
Wants to move to the right, so the friction's going to the left of the rope on the pulley.
The force on the pulley?
Because the rope is touching the pulley,
Yes.
so,
You missed a key thing.
did I?
well, isn't the force on the rope when I go down?
Why down?
Because it's going down.
Oh, okay. Yeah, but that's not the friction.
Okay.
Tell me about the rope. What kind of rope is it?
It is
A
ideal.
frictionless.
Frictionless.
Yes.
Oh, yes, okay,
There is no friction acting here because it's an ideal rope.
okay, so.
But if it wasn't an ideal rope,
If it's not an ideal rope, what you end up doing is you would treat, there are two frictions acting on the pulley. One friction is acting, the pulley's gonna rotate that way. There's a friction acting this way and a friction acting that way. Wait. No, sorry. Thinking. Strike that. What you would have is there's friction acting sort of all along there at a curved angle. So there'd be some friction acting this way, that way, that way, that way, and so on.
So there's no friction on box.
And then, oh, wow, I'm on the roll here. Try that again. The friction, since the rope is going that way, friction would be acting like, there'd be some friction acting this way, that way, that way, that way. And on the pulley, it'd be acting this way, that way. However many small ones you want to put in. But we'll keep it simple. Is there another question in there? As I was going through my variations of answers?
So no friction for box B, because it's hanging.
Right, friction, no friction
Okay.
for box B. Maybe, and I'll explain the maybe in just a moment.
Okay.
I'm not drawing any friction forces on B, that's for sure. All right, let's talk about tension. Tension is a pulling force. So first off, I know there's gotta be tension at the end of the ropes. There's tension throughout, but all I care about is the tension at the ends. So there's gonna be tension pulling on the rope. It's gonna be pulling this way on the rope. So I put my little tension notation right there. Well, what's pulling on it? What's pulling on the rope on this end?
B.
Yeah, so there's gotta be a force acting on B in the opposite direction. If you cut the rope here and this tension disappeared, box B would have only its weight acting on it, it would be in free fall. Let's go to the other end. I know there's gotta be a tension pulling in this direction. Where's the other part of that pair?
A. But
So
would
this-
you I'm sorry, would you label it B and A?
Oh, the
As
subscripts?
T,
Okay.
yeah,
If it's an ideal rope,
okay,
then the tension here and the tension here happen to be of equal magnitude.
okay.
So you don't need to do it. If you did want to put in subscripts, and some students do, if you want to put in subscripts, then these two would have the same subscript, so B and B, and this would be, say, A and A, or however you're going to label it. But since it's a single rope, I don't need, a single ideal rope, I don't need to. If I have two ropes, I definitely need I need at least two subscripts. All right, so let me address the maybe. I have a mass that is hanging here from a string. Actually, I have it right here. In this particular situation, what is the actual force between the string and the hook here? Well, looking at it, you basically have string tied to it, and the hook is sitting on top of the string like that. In that case, that is a normal force that is acting between the string and the hook. Now, it's also possible that my mass is sitting here and the string is embedded in it like this, in which case it's a friction force that is holding it in place. I did not tell you how the rope or string is attached to this mass here. We don't know. Could be a friction. It could be the normal force, depending on how it's connected. If I don't tell you, that's what we're labeling as tension. And I believe one of the videos I did was no such thing as tension or something like that. And I have heard some arguments based along this line that tension doesn't really exist. But unless I gave you more information about how it's connected, we don't know the exact force, and that's what we're calling tension. So when you see the rope attached to something, that's tension. Now, if that bothers you, then I guess on a test you could always ask how it's attached. But again, unnecessary work. Any questions?
When would we have the test?
Pardon?
When would we have the test?
After we're done with chapter 5. I don't know when that's gonna be. You'll know it won't be a surprise.
So there's only one test?
No, there's more than one test.
Okay.
There'll be typically 3 test grades. Are you in a hurry to get test 1 done?
I was just asking.
If you wanted to do it quickly, we could go faster.
Okay.
Okay. Just trying to meet your needs.
So you're saying in some problems they would explain what the tension, what's holding the, let's say, weight? And how would that show different, like how would you show that in an example?
If it were
For
a
tension.
different amount of weight?
Yes.
Is that what you
Or
said?
like what's attaching it?
Oh,
Like would we ever have an example that's like?
I haven't,
This is
I've
what-
never actually cared about that.
Oh,
The
okay, okay.
rope is attached somehow.
Just somehow.
I'm just throwing that out there because,
Gotcha.
you know, if you start reading,
Yeah.
there's no such thing as tension, you might go, wait a second, he said there was.
Just, okay.
And also I've had some students go with the argument of, it's touching it, so shouldn't there be a normal force? Well, no, not necessarily.
That's kind of what I thought at first when we were talking about it, but now I understand. Yeah.
I'm gonna do the double ramp, and then we'll do the test level problem. Any questions before yours? That still holds, so we'll keep that. I want to do friction last on this. Alright, so the objects, I have object A, object B, I have pulley, bless you, I have the rope, I have the pulley, which I'm going to make part of the ground. There we go. 4 objects. Let's start out with weight.
Sorry. So, box A to the ramp, or to the ramp.
Listening for the word on.
Okay, box A on ramp.
How am I drawing my arrow?
Now,
On.
the ramp.
So, like that?
No,
You just set down on the ramp.
you're right. I need to
Okay.
get better at my wording with this.
And I do recognize that the way some people say it and the way they would draw it are not necessarily the same thing.
Yeah,
All right, so I'm drawing weight down on what?
the box.
Yeah, the box. Comes in pairs, so there's gonna be another one.
Up on the ramp.
Okay.